And it was late last night for it because I taught at IUK last night, so it was late by the time I got home and everything. But yesterday's lecture is online, so if at any point in time, if you were in the room, which is not you guys, if you were in the room yesterday and you missed a portion because of picture day, all right, that video is up and ready. You can go back and look at it. All right, so today what we're going to do, we're going to take a look at limits. Okay, now we did limits last year, right? We looked at limits from a pictorial standpoint last year. It's the only thing we did. We just, okay, we've got these functions and we can graph them. And then we talked about the limit coming from the left, the limit coming from the right. And then what, for a limit to exist, the limit from the left has to equal the limit from the right. Okay, so hopefully we've already got that down pat. All right, but now what we're going to do, we're going to take a look at our limits, obviously from a graphical standpoint. We're also going to take a look at our limits from a numerical standpoint, as in I ought to be able to look at an XY table and then see what those numbers are doing, okay, because the graph and the numerical XY table should match. All right, and then we're also going to do it analytically, or in other words, algebraically. I'm going to algebraically manipulate the function with my limit, and then I'm going to be able to calculate it that way. This is a really good topic to introduce those three things because the limits really lend themselves to the graphs. But everything that we do in calculus this year, we will look at from those three standpoints. And actually, we may even look at it in word form as well, so a fourth one, but we will definitely, every concept, I am going to do from a graphical standpoint, from an algebraic standpoint, and from a numerical standpoint. All right, so that can help you. Maybe you're not getting the algebraic part, but when I show it to you in a graph, it all of a sudden makes sense. That may help with the algebraic part. Or you're not getting it from a graph, but you can get it when you look at the XY tables and the numbers just seem to make sense to you. All right, so that's where we're going to do with this. We're going to take everything three ways. All right, so August 26th. All right, we're going to take section 1-2, but this is going to be day one. All right, I'm going to take this section and we're going to cover it in more than one day. Okay, just so that we can break things down. All right, now I am going to review the graphical standpoint. We did it last year, but let's just take a look and practice that because we have slept since then. So a graphical approach, all right, to limits. I'm going to turn my fan on because I'm already hot. All right, so to be able to do this, and you're going to have a picture, okay? So let's attempt to sketch a little picture here. I'm going to try to do as many weird things in this graph as I possibly can. All right, I am going to assume that this graph is going to be called f of x when I get it done. Let's say we've got a vertical asymptote at x equals -2. Part of our graph is going to be doing that. Let's say we're going to have a closed dot there at 0 and 1, and then another portion of the graph is coming up and doing this. So I've got an open dot at 1, 1. Let's put an open dot at 0, 4. Let's say the graph is connected right in there. Let's say at 3, 2, I have a point. Let's go ahead and try to label that one because since we're not doing this on graph paper, I don't know how accurately that's going to come off. And then let's say that part of the graph does this. All right, so what type of function is this? Someone said it, I think, in the room. Piecewise? It's in pieces. Okay, I got pieces. All right, so actually I've just got a lot of stuff going on in here so that we can talk about a lot of different things with our graph. Okay, so we've got to have a picture to look at. Okay, as I had said earlier, we done this last year. The limit from the left has to equal the limit from the right in order for the overall limit to exist. All right, so let's just start with this one right here. I'll try to write a bunch of these down here. Let's take a look at the limit as x approaches -2. And then I'm just going to do of f of x because we really don't know what that function is, right? I don't know what the actual algebraic function is. Ooh, you almost can't read that -2 the way I wrote it. Try to fix that. All right, so I have, since I'm not indicating on that limit whether I'm coming from the right or from the left, then I've just got to check both directions. Here's -2. As I come from the left, the graph is coming down here and it's going to negative infinity. Here's -2. As I come from the right, the graph is going to positive infinity. All right, so does the left and the right side equal? Nope, so this one is does not exist because the limit from the left and the limit from the right does not match. Okay. How about the limit as x approaches 1 of f of x? All right, the limit as x approaches 1. Check it, since again, I'm not asking you from the left, I'm not asking you from the right. You got to check both. Limit as x approaches 1. Dane, what we got? Yeah, it's going to be 1. Yeah, it is going to be 1. I can only half hear what you guys are saying. All right, as I'm coming from the right, here's 1. As I'm coming from the right, my y value that spits out is a 1. As I come from the left and I get infinitely close to 1, it again is going to 1. Just because that's an open dot has absolutely no bearing on it, because I don't want to know what the value of the function is. I want to know what the limit is as x approaches 1. Okay, so speaking of which, the limit as x approaches a value and the value of the function at that location. So what's the value of f of 1? It's an open dot, right? You're shaking your head no, so it's undefined. All right, so this is undefined. The limit as x approaches 1 and the value of the function at 1 have no bearing on each other. Okay, we talked a lot about that last year. Okay, so hopefully we're remembering that. And that's a really good example of that. Okay, let's take a look at what's going on right in here. Granted, it's my hand sketched here. All right, but what's going on right here? What am I trying? The graph's going to infinity, right? Okay, so this line on this side and this line on this side is going to get infinitely close to x equals 3, right? The imaginary vertical line of x equals 3. All right, will this ever cross right here? No, it can't. All right, even though I didn't draw the asymptote in there. Why? Because at x equals 3, the function is already defined. If this were to cross, if this were to like cross right there, would it pass the horizontal line test? It wouldn't be a function anymore, right? So in something like this, you've got both going up like this, okay? We can call this unbounded behavior. So this right here of going up infinitely can be called unbounded behavior. Did I talk about that last year? Did I use those words last year? Yeah, I'm getting no's on that. Okay. So some vocabulary there. That's unbounded behavior, because what's the graph doing? It's growing to infinity, all right, without bound. So we often refer to that as unbounded behavior. All right, now, technically, as I'm coming up here, wouldn't I have to lift my pencil and then come over here? All right, you might be able to say that's a jump. I really don't like to call it a jump, but it is. I had to lift my pencil. All right, but I like the unbounded behavior right there. All right, now, on this unbounded behavior, if I wanted the limit as x approaches 3, when I check from the left, it goes to positive infinity. When I check to the right, it goes to positive infinity. All right, I want positive infinity, okay? Because why do I want you to write down positive? I want you to write down positive infinity, because then that tells me what the graph's actually doing. It is a unbounded behavior going in that positive direction, okay? A lot of times, though, depending on your textbook, they may say, here, let's put some textbooks. They may say this limit does not exist. All right, and I actually think our Larson textbook does this. All right, now, why would that be? What can you tell me about infinity? versus 1. This limit up here equals 1, but I'm saying this one down here equals infinity. What can you tell me that's different between 1 and infinity? Dane? Yeah, hey, perfect. Excellent answer. All right. 1 is a number. All right. So they like it when limits give you an actual number. All right. This really technically, depending on how you want to argue it, it's a concept. Infinity is a concept. It's not a specific number. All right. So that's why some of your textbooks are going to say, okay, this limit does not exist. All right. For me, all right, I want you to write infinity because I want you to picture in your mind what that graph is actually doing. I don't know. How many more can we do on this? Could we do lots? I haven't done any one-sided limits. Let's review some one-sided limits. How about the limit as x approaches 0 from the left of f of x? All right, we haven't done any left-sided limits, just to review those. As it approaches zeros from the left, I'm going to get, everybody say it? What am I going to get? Maybe, do you know?
1.
I can't hear you. Not infinity. Josiah, you said 1. All right, as I approach 0 from the left, I'm coming this way. I'm approaching 0 from the left. As I get infinitely close to 0, it spits out a y value of 1. Okay, does that make sense? All right, now let's do the limit as x approaches 0 from the right. All right, so I'm still approaching 0 here. I'm coming from the right. I'm going to get infinitely close to 0. So really, I just need to look right in here as to what the graph is doing. And I'm approaching what y value? Okay. Yeah, 4. Okay. It doesn't matter that that's an open dot and that's a closed dot. It has no bearing on it whatsoever. All right, because we're just looking at what approximate y value comes out. All right. I don't know how many more we need to do of this. All right. What is f of 0? F of 0 is, Dane? Yeah, it's just 1. All right, again, this open dot has nothing to do with this. I want the value of the function at 0, so I go to my x-axis at 0, go up to the function, and it is a 1. All right, this is when we said the value, we haven't done f of, let's do f of 1. What's f of 1? Oh, I did f of 1 already. F of 1 is undefined, so I've done that one. All right, can anybody else think of any other questions on like this? We did lots of these last year, so I'm hoping that that's enough review on those. Okay. Now let's take a look at a special one. My drawing of this is not going to be good. Let's write down a common limit that fails to exist. All right, we are going to have graphs, all right, of functions. Let's say we've got the limit as x approaches 0 of, say, sine of 1 over x. I put an actual function in there. All right, and a lot of times I usually leave this notation off, but sometimes they'll put little square brackets or round brackets around that just to isolate the function from that limit notation. All right, now on this, if we were to look at this on a graphing calculator, okay, I'm going to attempt to draw it. It's going to be horrible when I attempt to draw it here by hand. All right, but what happens is I've got the graph, it's coming in, and then all of a sudden it does that type of thing, and then it starts doing the same. So in other words, right around here, as x approaches 0 in the graph, I have what is called oscillating behavior, because sine's going to bounce back and forth in between 1 and -1. So this is oscillating behavior. All right, and like I said, if you had your graphing calculator, you plug that in real quick and you graphed it, I would probably zoom trig. All right, on your graphing calculator, I would definitely zoom trig so that you get the actual picture there. It's going to be better than just hitting the plain graph button. You're going to see some oscillating behavior right there. All right, whenever you have oscillating behavior in a graph around the limit of whatever value it is approaching, then we're going to say it does not exist. All right, that's just one. This is just one example of a graph that does that oscillating behavior. There are others. Okay, so from a graphical standpoint, a special one. All right, now let's go ahead and do a numerical approach. Okay, now initially, I am going to draw the XY table left to right, as opposed to up and down. Don't we normally draw XY tables up and down? If you look at your X and Y table in your graphing calculator, it's going to be up and down because traditionally that's the way we draw our XY tables. All right, however, I'm going to do them horizontally because why? When we're looking at limits, we're coming from the left or we're coming from the right, right? So if instead of doing this up and down, if I draw it this way, it's going to relate more closely to what we do from a graphical standpoint. All right, so let's say I've got the limit as x approaches 1 of x to the third minus 1 all over an x minus 1. Okay, so what I'm going to do, let's put that there. I'm going to make an XY table. And I'm going to call it x, f of x, same thing as xy. It doesn't make any difference. This function notation, we're assuming that's function is going to be called f of x. Okay, now, I want this limit as x approaches 1. So that means I do have to check coming from the left. I've got to check coming from the right. So in the middle of my table, I want to put my 1 because I want to be able to check values coming from the left. I want to be able to check values coming from the right. This is what I'm trying to figure out from a numerical standpoint. All right, now I need to get infinitely close to 1 on the right-hand side. So I need to pick values that are just a little bit bigger than 1. All right, so I don't know, 1.001. All right, then maybe I could go out to 1.01. All right, maybe 1.1. I'm getting farther and farther away, okay? But I'm still pretty darn close to 1. If I create the XY table and I put those values in for you, it's going to be a little bit easier. Once at some point in time, I'm going to make you pick values on both sides, okay? What would be a really close one over here? I got to get smaller than 1, right? But I want really, really close to it. I don't know, like 0.999. Is that what you're thinking, Dane? 0.999. I mean, I could 3 places. That's probably good enough. I could maybe do a 0.99. I could do maybe say a 0.9. I'm still getting infinitely close to both sides. All right, now if you want to make your life easy, obviously at this point you'd grab your calculator. I'm going to let you use your graphing calculator. You'd put this into F1. F1. You'd put this into Y1. Yeah, it's early this morning. You're going to put this into Y1. You're going to have that set on ask. You're going to put those values in. It's going to spit them out for you. All right, so let's say we're going to get like a 2.71. If I did not screw this up, we should get a 2.97. We should get a 2.997 right there. Over here, we're going to get a 3.003. We're going to get a 3.03. We're going to get 3.31. Okay, looking at what those numbers are doing, these are getting really, really, really close to 3. And these going this way is getting really, 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 really close to 3. So this limit is 3. Okay. And we're doing the exact same thing. Now, obviously, if you're looking at it from a graphical standpoint, like I said, and you're using the calculator and you're looking at that XY table, it's going to be up and down. It's not going to be horizontal. But same concept. All right, do I need to do more than just one of these? Okay, this is just kind of looking at it from a numerical standpoint. I don't always do this. Sometimes when I find the limit is going to unbounded behavior, all right, I will definitely look at that XY table and just plug in some numbers as like x approaches infinity if I want to see what that end behavior is, okay, because then I can real easily see what the numbers are doing. But I would venture to say that numerical approach is probably the least one that I use. It's the one I use the least. It does come in handy depending on what the situation is. Okay, now we're going to take an analytical approach, okay, or an algebraic approach. Analytical approach to limits. So basically this means we're going to just work out some algebra. All right, now obviously in this beginning section here, we're going to do the really easy ones, okay? And I don't even think that they're going to do hardly anything. Nope, they're not going to do anything that's really challenging in this first section because we're just like baby steps. We're going to start off baby steps. We're going to do the limit as x approaches 3, and then we're just going to do, say, 2x minus 5. And again, in your textbook, they might put a set of parentheses around that. They might put square brackets around that function. I have a tendency to leave that off every time I write that. All right, now we know that's a line, right? Straight line goes through -5, positive slope. All right, so it's definitely gonna have a value, isn't it? Okay, how am I gonna find out as x approaches 3? Think algebraically. What am I gonna do? How am I gonna find that y value? I know what the function is. Can I just plug it in and it's gonna spit out a y value? Okay, that is called direct substitution. All right, this is just a straight line, nothing fancy. I'm going to put ds on here. All right, for direct substitution. And I can't spell direct. Let's fix that. Okay, direct substitution. So when I do a direct substitution, I am actually taking the limit. So the limit as x approaches 3 goes away. All right, if I do a direct substitution in my next line of algebra, this notation has to go away. And I'm just going to write down 2 times 3 minus 5, because I'm going to be 6 minus 5. That's going to give me a 1. So direct substitution. Notation is going to be extremely important. If I do any type of, later on when I do a little bit harder ones, if I'm doing algebra manipulation to this function, I have to keep this on every line of work I do until I get to my direct substitution. When I get to the direct substitution, from here to here, doing the direct substitution, you're taking the limit. When you take the limit notation goes away. Okay? All right, so let's do like the limit as x approaches a -8 of the cube root of x. Okay, so again, direct substitution. That's one of the very first things we are always going to try. All right, so I'm going to be doing a direct substitution. When I do that, I'm going to take the -8. I'm going to plug it in. Cube root -8. We know that one because numbers are small, -2. I'm not trying to make the math hard here. I'm just trying to show you the algebra concept. Okay, so let's do one more. Let's do the limit as x approaches, say, 7 of the absolute value of x minus 9. All right, just like basic, nice little functions that you can't do much with. There's a little absolute value. All right, I want to take the limit. I want to do a direct substitution. When I take that limit, the limit notation goes away. All I have to do is plug in the 7, absolute value of 7 minus 9, which is going to give me a -2 inside those absolute value bars, which is then going to take me all the way down to a 2. All right, so on this very first one, they're just trying to get you to look at the 3 different ways to evaluate limits. They're going to do very, very easy ones. Okay. Now let's, just in case, I do want to like take a different approach, and I want to make you do a little bit of thinking today. All right. Do I know what this graph is? It's a V, right? It's been shifted to the right 9. All right, so I don't have any, it's all reals, -infinity to infinity for my domain, correct? Okay, so I'm going to be able to get an answer. Cube root, we know what that looks like, right? It looks like the square root with the tail. All right, not shifted away from the origin at all. So this is my domain is -infinity to positive infinity. Same thing there with my line. Okay. I want to make sure that you don't get yourself in trouble. So let's put graphing calculator. I mean, because you are going to have to think. I don't know that this is going to come up in anything you do today, but it will come up at some point in time. Now, let's suppose I did, like, say, the limit as x approaches 9 of x minus 9 over the square root of x minus 3. And like I said, I don't know if they're going to do this to you today or not. We will encounter it at some point in time. All right, since I've showed you 3 ways, unless I specifically am wanting you to do a specific method, I'm going to let you use the process you want. All right, sometimes on tests, I'm going to say use an analytical approach, or I'm going to say use a graphical approach. If I don't specify and I just say, okay, here's a limit, figure it out. You can choose whatever method you want. So if you really like the graphical method, you could do that. If you really like algebraic, you can do it that way. All right. So let's assume that you like looking at it from a graphical standpoint. All right. If I put this in my graphing calculator, I even think that this is going to happen even with the newest ones. All right. I get something that looks like this. Standard graphing window. It kind of looks like that. Or at least it does on mine. I mean, I've got the thicker graphing color calculator. I don't have the thin ones. So I'm pretty sure it looks exactly like that. Dane, you've got your graphing calculator. Yeah, it looks just like this, doesn't it? Okay, which if just looking at that picture, all right, what here would be 9. All right, so technically, should I be able to find an actual value for this limit, right? And if you just go from your picture, you could. All right, we're going to have a rule in here that's going to say thou shalt not trace. All right, I've never even, last year when I was teaching you the graphing calculator, I never even told you there was a trace button on there. Okay, and thou shalt not trace. We are not going to trace. If you have discovered that button on your own, your little cursor, you can just move along that curve. All right, and you can trace. All right, we don't want to do that because let's stop and think about this function. It's a rational function, right? If it's a rational function, could I do real quickly? Could I take a look at the domain? All right, rational functions, if I want to find the domain, what do? We take the bottom and set it equal to 0. Denominator. Yeah, denominator. Very good, Josiah. We take that denominator and we set it equal to 0. All right, so what would I do? I would add 3 to both sides, so square root of x equals 3. I'd take square both sides. I'd get an x equals 9. And then if I'm trying to find domain here, then what is it about this value? It's an excluded value from the domain. So technically those probably should have been not equal to all along. All right, so in other words, if I put 9, if I let x be 9, that means my denominator turns out to be 0, right? So my domain at 9, is there going to be a closed dot? There is not going to be a closed dot, okay? Your graphing calculator, and maybe if you zoomed in at the newer ones, might show the dot. I don't know if it does or not exactly, but technically the real graph, all right, is going to do this, but when it gets to 9, there's going to be a hole there. Okay, but then there again, let's go back and look at it from an algebraic standpoint, because at that still looks at that to me, if I'm just using the graph and I understand that 9 is not in my domain and I'm thinking, okay, there's my graph, then I ought to think, oh, I can still come up with a value, right? Because I think if you do use your trace, I think this is about 6. All right, so you're going to think, oh yeah, so my limit is 6. All right, but let's do a direct substitution. All right, let's do an analytical approach. Let's take an analytical approach. All right, if I take an analytical approach, I've got the limit as x approaches 9 of x minus 9, square root of x minus 9. Okay, so what have we been doing? We've been doing direct substitution because that was the first thing I showed you. All right, so that means I'm taking the limit. The limit notation goes away. I plug in 9, so I get 9 minus 9 over the square root of 9 minus 3. Well, 9 minus 9 on top gives me a 0. Square root of 9 minus 3, that's going to be 3 minus 3. That's going to give me a 0. Well, first of all, can we divide by 0? We already know we can't divide by 0, okay? But we, up to this point, have not encountered a 0 on the top. We've never encountered 0 over 0. Okay, so for right now, because we're not there, I just want to show you how you can intertwine all of these different things. You got to think about the function, you got to think about that, everything that I've ever taught you. Okay, right now, I don't know, let's just say that we're getting, this is an oops, we don't know how to deal with this. Later on, you're going to learn that this is an indeterminate form, okay? But for right now, because we're not quite there yet, but I want you to start thinking about what is happening. Sometimes even on the same problem, you may not have to pull in some pre-calc knowledge like finding the domain. You may need to look at it from your graphing calculator. You may need to work it out algebraically. Okay, so right now, I mean, ultimately, this is going to be an indeterminate form because I get 0 over 0. So we would do something else to get the answer. Okay, we would do something else to get the answer. But just it all plays into part. You can't forget anything we've ever done. Okay. All right. So said I wasn't going to do a lot of thinking things today. This is a little bit of thinking. All right, a little bit of thinking won't hurt you. All right, now something. Did we do that? Did I make you sketch? I did not make you sketch functions when I gave you a bunch of rules last year, did I? You never, like I didn't give you a bunch of limits and function values and vertical asymptotes and then say, okay, sketch the function. No. Okay, you're shaking your head. No, we did not do that. Okay, this year we're going to do this. All right, I want you to kind of play around with this. Okay, I want to be able to give you true things about a function. And then I want you to sketch a possible, what it looks like from a graphical standpoint. Okay, so it's going to say sketch, and I could say sketch a possible graph, because technically, depending on how you draw your graph, people could have it right based on the information I give you, and it still not match somebody else's, okay? So you're going to sketch a possible graph, all right, of a function f that satisfies the given values. Okay, important keyword here. I told you have to sketch a function. If you have to sketch a function, it has to pass the vertical line test. Okay, so vertical line test. So when you get done with your picture, you should try that vertical line test and see if it passes. Because if at any point in time it fails, you didn't do what it said to do. All right, now what's going to happen is I'm going to give you true things. All right, and I can actually, at this point, I can give you lots of information. I could tell you that f of 1 is undefined. I could tell you that the limit as x approaches 0 of f of x equals -2. I could tell you that f of -1 equals 6. I could tell you that the limit as x approaches 2 of f of x equals 3. So I get, like right now, because that's what we're doing a lot of, we're doing a lot of function values and limits. So those are the things that I'm going to tell you. All right, now what I would do, you just got to start. This is trial and error. You got to start somewhere. Look at your first thing right there. It says f of 1 is undefined. All right, so think of some ways. What could the graph look like at f of 1 for it to be undefined? I could have a hole. I could have a hole there. Josiah, what'd you say? Yeah, I could also have a vertical asymptote. All right, so that's how you're going to have choices in what you do. Okay, you're going to have choices. All right, so I don't know, f of 1, I don't know, I'm going to put let's put a hole. Let's put a hole there. I'm going to put a hole. You can put a vertical asymptote if you want. Okay, now the limit as x approaches 0 of the function has to be -2. All right, so here's 0. As I approach 0, the value of that limit has to be -2. So that means that coming from the left and coming from the right, I've got to hit -2 at 0, right? So, and I know I'm going to have to come up here somewhere, so I might do something like this. All right. And then I can do just about anything. All right. I could keep going down maybe, or do I necessarily want to keep going down? Because if I look right here, this says f of -1 is 6. All right, well, f of -1, I've got to get from here back up to there, right? So could I come down and have a cusp right here and then come back up and go through that point right there? So then I've met f of -1 is 6. I've met my limit as I approach from the left as x, at the limit as x approaches 0. I come from the left as -2. I come from the right, -2. I've hit this. I've got f of 1 is undefined, so I can have a hole there, or I could have a vertical asymptote. Your picture might be a little bit different there. Now on this one, the limit as x approaches 2 has to be 3. Okay, well, here would be, let's rough estimate 3 there. Probably didn't do it very, very good there. But technically, what could I do? I got to get the graph going through there. So could I come up here and then take a sharp turn and go that way? This wouldn't really be at 3. Let's put that dot a little bit below there. Because technically that open dot could be anywhere, couldn't it? So if I had it down here a little bit, could I say, okay, it comes up here, I got an open dot here, and I come up here. Now is the limit as x approaches 2 coming from the right, coming from the left? Am I approaching 3? So, yeah, I got that. I've got this, I've got this, I've got this. Now, does it pass the vertical line test? It passes the vertical line test. All right, one possible picture. Okay, one possible picture. Okay, this will be challenging to begin with until you get used to it. It is trial and error. You just got to like play around, make everything true, see what your function looks like. Okay, and actually, the only reason we're doing this is conceptually. Do you understand what this limit idea means? Do you understand when function values have a value or they're undefined, and how can all these pieces and parts play together? Okay, how can they play together? There are lots of practice questions of this on my website. All right, we've got lecture notes and videos. Then you'll have a section for your worksheets. All right, there also is going to be a section labeled, practice worksheets probably, or practice reference material. All right, and there will be answer keys for them. So like if you want me to have practice problems of this, download those, try them, and then check them with the answer keys. All right, because this usually is something it takes a little bit more practice. I mean, in your homework, you may have one question. All right, whereas you're going to need more than to do just one to get the hang of this. All right, so actually, I think I'm good with everything for our limit.